The engineer sees the pickup truck at 11 seconds. That is not a guess. That is roughly what the geometry allows on a straight stretch of main line at dusk, with headlights carving a cone into the gloom and a grade crossing sitting a quarter-mile ahead. 11 seconds from the moment a shape resolves out of the background into something that should not be there. He does everything correctly. He sounds the horn. He watches for the truck to move, because almost every time it moves. Then it does not move, and his left hand goes to the brake handle, and he pulls it all the way over into the emergency position. And 18,000 tons of steel behind him begin the slow business of deciding whether to stop. They will not stop. Not here. The impact happens roughly 9 seconds later, and the train finally comes to rest somewhere between 4,000 and 6,000 feet past the crossing, which is to say more than a mile down the track from the point where the engineer first understood what was about to happen. Every safety campaign in the country repeats the same line. A freight train needs a mile to stop. People hear it, nod, and file it away as a statistic. But almost nobody asks the obvious follow-up question. A mile is an enormous distance. A loaded passenger jet lands and stops in less. A fully loaded highway truck at the same speed needs maybe 400 feet. So where does the rest of it go? Because that mile is not one mistake. It is not a design flaw waiting for a clever engineer to fix. That mile has been divided up piece by piece among a series of physical facts and historical decisions that all made perfect sense at the time. Some of it belongs to human perception. Some of it belongs to compressed air moving at the speed of sound. Some of it belongs to a few inches of slack in every coupler on the train, and some of it belongs to the microscopic patch of steel where wheel meets rail, an area you could cover with a coin. So let us take that mile apart. Not travel it the way the train does, but audit it foot by foot and find out exactly who owns each piece of it. The first several hundred feet belong to a person, not to a failure of that person, to the simple mechanics of being a human being in the front window of a very large object, trying to interpret the world at 79 feet per second. Locomotive engineers spend their careers reading distance. They know their territory the way a sailor knows a channel, and much of the job is anticipation rather than reaction, because reaction on a railroad is nearly useless. But a grade crossing is a specific kind of problem, because the vast majority of the time, the thing in the crossing clears. Cars roll off the tracks. Pedestrians step back. Trucks that appear to be stopped are actually creeping forward. An engineer who dumped the air every time something looked wrong at a crossing would spend his entire shift stopped and would tear his train apart doing it. So there is a judgment window. It is not indecision. It is expertise. And it is the same expertise that keeps freight moving on a network with more than 200,000 places where a road crosses a track at grade. The engineer is running a probability calculation that is correct almost every single time. Then comes the recognition that this time is different. Then the horn, because the horn is the only tool that can actually change the outcome, and it is far more likely to work than the brakes are. Then the hand on the handle. Add those together and you have burned somewhere between 3 and 6 seconds. At 55 miles an hour, that is 400 feet, and the train has not yet begun to slow down at all. It has not even been asked to, and that assumes he can see the crossing in the first place. Sight lines from a locomotive cab are not generous. The nose of the unit blocks the near track ahead. A curve puts the crossing behind a tree line until the last few hundred feet. Cuts, embankments, buildings, standing cars on an adjacent track, sun low on the horizon in the direction of travel. Every one of these compresses the window. The driver's side of the equation is no better, and in a stranger way. Approaching trains are notoriously difficult to judge, because a large object heading directly toward you produces very little apparent lateral motion. The mind reads size as distance and slow visual change as slow speed. A locomotive doing 55 looks from a stopped car at a crossing, like something with plenty of time left in it. That misjudgment is not carelessness. It is a genuine limitation of human depth perception, and it kills people every year. And here the story stops being about a person, because the request the engineer just made does not travel through wire or hydraulics or anything electronic. It travels through a pipe full of air, and it moves at the speed of sound in that pipe. And that is where the next enormous slice of the mile disappears. To understand why a modern freight train still communicates with its own brakes using compressed air, you have to go back to a time when it communicated using shouting. For the first several decades of American railroading, stopping a train was a manual task performed by men on the roof. The engineer blew a specific whistle signal. Brakemen, spaced along the train, climbed out onto the tops of moving freight cars, gripped an iron wheel at the end of each car, and cranked it down using a wooden club for leverage. Wheel by wheel, car by car, they screwed brake shoes against wheel treads by hand. They did this at 15 or 20 miles an hour, in the dark, in the rain, in blowing snow, on roofs 12 to 14 feet above the ballast, with no harness and nothing to hold. They ran between cars on planks. Railroads hung ropes across the right-of-way ahead of low bridges and tunnel portals, so a man sprinting across the roofline would feel a warning brush against his face before the masonry took his head off. The casualty numbers from that era are the kind that stop conversations. Brakemen were maimed and killed at rates that later generations of workers would refuse to accept for any wage. And the braking itself was slow, uneven, and frequently insufficient. A short train might take several hundred feet to stop from under 30 miles an hour, assuming the crew got to their posts in time. The fix arrived in stages, and the crucial insight was not the compressed air itself. It was the logic behind it. An early air system simply pushed air from the locomotive down the train to shove the brakes on. That worked, sort of, until a hose burst or a train broke in half, at which point every brake on the train released at once and the cars ran wild. So the logic was inverted. In the automatic system that emerged in the early 1870s, the pipe running the length of the train is kept charged with pressure, and each car carries its own reservoir. A drop in pipe pressure is the signal to apply. That means the failure of the system, a parted train, a ruptured hose, a broken pipe, applies the brakes instead of releasing them. That inversion is one of the most elegant safety ideas in industrial history, and it is still the operating principle under every freight train in North America a century and a half later. But elegance did not equal speed. The early automatic brake still applied the front of the train noticeably before the back of it, because the pressure drop had to crawl down the pipe from the locomotive. On a long train, the difference could be measured in tens of seconds, which produced exactly the sort of violence you would expect when the front third of a train slows hard and the rear two-thirds are still coming. In the mid-1880s, a railroad industry association ran a series of freight brake trials at a division point in Iowa, using strings of 50 cars. The trials became legendary partly because they went so badly. Competing systems were tested, and the results ranged from disappointing to alarming. In one emergency test, the deceleration was violent enough that observers riding in the rear car were thrown the length of it. An Iowa State Railroad commissioner named Lorenzo Coffin had been hounding the industry for years about brakes and couplers, and he kept the trials alive when nearly everyone else had lost interest. On one day of testing, he was reportedly the only state commissioner still standing at the trackside. The result of that public failure was a redesign. The valve on each car was reworked so that the car did not merely receive the signal, it repeated it, venting its own air locally the moment it detected an emergency reduction. The pipe itself was enlarged. Instead of a pressure drop that faded as it traveled, the train now propagated its own emergency signal down its length, each car shouting to the next. Congress made the whole package mandatory in 1893, with a compliance deadline the railroads pushed back twice while pleading poverty. By the middle of the following decade, roughly 2 million American cars and 89,000 locomotives carried the system. Now here is why all of that history is standing in your mile. An emergency application propagates down the brake pipe at somewhere in the neighborhood of 900 feet per second. That is fast in human terms and very slow in railroad terms, because a heavy freight train is a mile long. Do the arithmetic and the signal takes 10 to 15 seconds to reach the last car. Sit with that number. 10 to 15 seconds after the engineer commits, the rear of his train has not yet been told anything at all. Those cars are still rolling free, still pushing, still delivering their full momentum into the cars ahead of them, which are braking. Modern practice softens this. Distributed power units placed mid-train and at the rear vent the pipe from their own position on a radio command, so the signal enters the train in 2 or 3 places at once instead of one. An end-of-train device can do something similar from the last coupler. These help enormously, and they are the reason contemporary long trains handle as well as they do. But they do not eliminate the delay. They only cut it into shorter pieces. A service application, the ordinary controlled brake reduction an engineer uses hundreds of times a shift, is even slower to travel, which is why train handling is taught as an act of forecasting rather than control. You are not braking where you are braking where you will be in a minute. Call the propagation delay another 800 to 1200 feet of your mile, gone before the whole train is even participating. And it gets worse, because those cars are not rigidly connected to each other. They are connected loosely, on purpose, and that looseness owns the next piece. Look at where 2 freight cars join. The knuckle couplers themselves have a small amount of built-in clearance, so they can engage reliably in a yard, in the cold, on a curve, with a car rolling in at a couple of miles an hour. Behind each coupler sits a draft gear, a spring and friction pocket designed to absorb shock, and it permits several inches of travel in each direction. Add it up, and every joint in the train has something on the order of half a foot to a foot of free play. In a 100-car train, that is roughly 50 feet of slack distributed along the consist. That slack is not sloppiness. It is essential. No locomotive on Earth can start 15,000 tons all at once, because breaking every car free from standstill simultaneously would demand a pull that would simply tear the couplers out of the cars. Instead, the engineer eases forward. The locomotive takes up the slack one joint at a time, and the train starts in a rolling wave. The rear car begins moving nearly a car length after the front one does. But slack that helps you start is slack that hurts you stop. When the head end breaks and the rear end has not yet received the message, those 50 feet close. The train bunches. Cars run in against the cars ahead of them, and the energy of that run-in has to go somewhere. Sometimes it goes into a knuckle, and the knuckle breaks, which, incidentally, causes an immediate emergency application because the pipe parts with it. Sometimes it goes sideways. On a curve, buff force pushing forward through a string of cars can shove the middle of the train toward the inside of the curve like a bowstring pulling straight and lift cars off the rail. Railroaders call it string lining, and it is one of the reasons a heavy train on curving territory is handled with such caution. This is the part that surprises people who assume emergency braking is always the right answer. It is not. Dumping the air on a long train in the wrong place, cresting a hill in a sag, midway through a curve, with the slack in the wrong condition, can derail the train you are trying to save. Engineers are trained accordingly. The emergency application is a last resort, not because anyone is precious about it, but because the last resort has its own body count. So even after the signal has propagated, the train is not decelerating cleanly. It is compressing, surging, and absorbing its own length before the retarding force becomes uniform. There goes several hundred more feet, which brings us to the most fundamental piece of the mile, and the strangest one, because it is not a limitation of the brakes at all. The brakes are not the problem. They can lock every wheel on the train solid. The problem is what happens where the wheel touches the rail. A steel railway wheel resting on a steel rail does not sit flat on it. Both surfaces deform very slightly under load, and the actual area of contact is astonishingly small. For a loaded freight car, something in the neighborhood of a coin, sometimes described as being about the size of a dime, every ton of that car is funneled through that patch. That tiny, hard, barely deforming contact is the whole reason railroads exist. A rubber tire flattens against pavement, flexes constantly, and wastes energy as heat with every rotation. Rolling resistance for a highway vehicle runs around 1% of the load. Steel on steel runs closer to 1/10 of that. It is the single most efficient way humanity has found to move enormous mass across land, and it is why one crew can move freight that would require several hundred trucks. Now flip it over. The same property that lets a train roll forever with almost no resistance means it has almost nothing to grip when you want it to stop. The measure that matters is the coefficient of adhesion, how much horizontal force that contact patch can transmit before it starts to slide. On clean, dry steel at low speed, it lands somewhere around 2 to 4/10. That number is a fraction of what a rubber tire achieves on dry asphalt, and it sets an absolute ceiling on deceleration. You cannot brake harder than the rail will let you push, no matter how good the brake shoes are. And that ceiling is not stable. Water on the railhead drops it sharply. Oil or grease drops it catastrophically. Laboratory work on wheel and rail contact has recorded the coefficient collapsing to around 6/100ths under oil contamination, roughly 1/10 of the clean, dry value. Crushed leaves in autumn bake into a slick black film that has stranded trains across entire regions. Frost, light drizzle after a dry spell, spilled grain at an elevator, the residue where a locomotive dropped sand and someone else's wheels polished it in. All of it changes the arithmetic under your train while you are standing on the brake. Exceed the available adhesion, and the wheel stops rotating and starts sliding. That is worse than useless. A sliding wheel provides less retarding force than a rolling one on the edge of slipping, and while it slides, it grinds a flat spot into itself. A flat wheel then hammers the rail for the rest of its trip, damaging track, damaging bearings, and eventually forcing the car out of service. So the design target is not maximum clamping force. It is the largest force that reliably stays just short of a slide, on wet rail, on worn wheels, on a bad day. Which means the braking system on a freight train is deliberately calibrated for the worst realistic surface it might find, not the best. Railroads do fight back against the adhesion ceiling, but only where they can reach it. Every locomotive carries sandboxes and nozzles aimed at the rail just ahead of the leading wheels, and dropping sand can lift the available grip substantially. Modern units add electronic slip and slide control that senses a wheel set losing its footing and modulates the effort at that axle within a fraction of a second. Both of those live on the locomotives. Behind the locomotives sit 100 freight cars with no sanders, no electronics, and no way to know what the rail is doing. 90% of the train's mass is braking blind on whatever surface it happens to find, and that is the mass that decides where the train stops. There is one more physical fact hiding under all of this, and it is the one that scales fastest. Kinetic energy rises with the square of speed. Double the speed, and you have quadrupled the energy that has to be removed. A train doing 60 is not stopping in twice the distance of a train doing 30. It is stopping in roughly 4 times the distance, which is exactly what the operational guidance reflects. About half a mile from 30 miles an hour, and something on the order of 1.5 miles from 60. If you are enjoying this, subscribe. We take apart the engineering and the history behind the railroad every week. All of that energy has to become heat, and it becomes heat in the brake shoes, and the wheel treads, and on the locomotives, in a bank of resistor grids overhead. Dynamic braking, where the traction motors are turned into generators, and the train's motion is burned off as electrical heat, does a great deal of the work in ordinary running. But federal rules are explicit on the point. The friction brakes alone must be capable of stopping the train safely under all operating conditions, without any help from the dynamic brake at all. Whatever the electronics contribute is a bonus, never a dependency. So the mile is spent. A few hundred feet on human recognition, 1,000 or so on the air working its way to the back of the train, several hundred more on the slack closing up, and the balance on a contact patch the size of a coin trying to hold back 12 million pounds without letting go. Except that the mile is not really a fixed number at all. It is a range, and the range is enormous. Weight is the obvious variable. An empty intermodal train and a loaded coal train are the same length and utterly different problems. Grade is the brutal one. Braking distance on a descending grade can stretch far past anything a flat track figure suggests, because gravity is now working the wrong side of the equation for as long as the descent lasts. Federal brake rules include a specific provision for this. On a descent averaging 1% or steeper over 3 continuous miles, a train that exceeds its authorized speed by more than 5 miles an hour must be brought to a stop immediately, by emergency application, if that is what it takes. The rule exists because the alternative, a heavy train accelerating downhill past the point where its brakes can recover it, has written some of the worst chapters in railroad history. Then there is heat fade on a long descent, brake shoes losing effectiveness exactly when they are needed most. There is rail temperature. There is the number of cars with brakes actually working, which is why the required percentage of operative brakes is regulated and inspected rather than assumed. There is also a limit on how long you can hold. A conventional freight brake cannot be partially released and reapplied at will. Releasing means recharging the reservoirs on every car from the locomotive's compressor, and that takes time the descent may not give you. Set too much brake too early on a long grade, and you arrive at the bottom with depleted reservoirs and nothing left to spend. Set too little, and you are chasing the train's speed with a tool that answers slowly. Mountain grades are where the theory of train handling stops being theoretical, and the rule books governing them are written in language that reads like a warning, because they were assembled, incident by incident, from the ones that did not work out. Change any one of those, and the mile becomes 3/4 of a mile, or 2 miles. That variability is precisely why railroads did not try to fix the stopping distance. They built the entire operating system around it instead. Consider what that means in practice. Nearly everything you can see beside a main line is an answer to the braking distance problem. Block signals are spaced according to how far a train needs to stop, not according to convenience. The whole logic of a multi-aspect signal system, a yellow before every red, and on many railroads a flashing yellow before that, exists so an engineer receives the information at least a full braking distance before the place he must be stopped. The signal is not telling him about the track ahead. It is telling him about the track 2 blocks ahead, because that is the only warning that is any use to him. Crossing warning circuits work the same way. Gates and lights do not activate when the train arrives. They activate when the train enters a defined approach section, calculated to deliver a minimum warning time before the train reaches the road. Drivers experience that as gates coming down with no train in sight and treat the delay as an inconvenience or an error. It is neither. It is the road being given the reaction distance that the train does not have. The same reasoning is painted on the right-of-way itself. Whistle posts are planted a fixed distance ahead of each crossing, so the horn sequence begins early enough to be useful rather than merely loud. Speed restrictions are posted well in advance of the territory they govern, because a sign at the start of a curve would be worthless to a train that needed to be slowing a mile earlier. Read the trackside furniture in order, and it is essentially a running commentary on stopping distance, written for an audience that has to act on information long before the reason for it becomes visible. Even the modern electronics are shaped around it. Positive train control, the overlay system that automatically enforces speed restrictions and stop authorities, works by continuously computing a braking curve for the specific train it is riding on. If the train crosses the curve, the system applies the brakes itself. Early versions of those algorithms were criticized for being too conservative, for predicting worse braking than the train could actually deliver, and slowing trains that were not really in danger. Research went into tightening the predictions, but the direction of the error was deliberate. A system that assumes a train stops shorter than it really does is a system that eventually finds out it was wrong at the worst possible moment. All of which raises a fair question. If the delay in the brake pipe is such a large part of the problem, why not simply send the signal electrically and apply every car at the same instant? That technology exists. It has existed for decades. Electronically controlled pneumatic braking runs a wire the length of the train and commands every car's valve simultaneously, in milliseconds, regardless of where that car sits in the consist. The air still does the physical work of pressing the shoes. The electronics only replace the messenger. Applications become graduated and releasable, which alone transforms how a train can be handled on a grade. Test results have shown stopping distance reductions of 40 to 60% under certain conditions. One major carrier publicly promoted that figure in its own materials. The federal regulator wrote rules to accommodate the technology and offered real operational incentives, including dramatically extended intervals between required brake inspections. In 2015, following a series of oil train derailments, the technology was mandated for certain high-hazard flammable unit trains. The industry objected on cost, arguing the mandate would run into billions of dollars for a benefit it disputed. A revised regulatory analysis concluded the requirement was not economically justified, and the mandate was rescinded in 2018. It is worth being precise about what that decision did and did not mean. The rescinded rule covered a narrow category of trains, not the general freight fleet, and nobody was ever proposing to convert 200,000 freight cars overnight. The genuine obstacle was never really the wire. It was interchange. American freight cars wander. A car built in one railroad's shop spends its life moving between the networks of half a dozen carriers, and a braking system only works if every car in the train speaks it. That is a coordination problem across an entire continent's rolling stock, and coordination problems of that scale tend to be solved by regulation or not at all. So the pneumatic signal remains. It still travels at 900 feet per second, and the mile stays a mile, which brings us back to the crossing, and to the number that makes all of this matter. In 2025, there were more than 2,200 collisions at highway rail grade crossings in the United States. Just under 300 people died. Roughly 760 were injured. Averaged out, something on a track is struck about once every 3 or 4 hours, somewhere in the country, all year. Now look at the detail inside those numbers, because it dismantles the mental image most people carry. The majority of crossing collisions do not involve a train roaring through at track speed. They happen at low speed, most of them under 30 miles an hour. In roughly a quarter of them, the train was already occupying the crossing when the vehicle struck it. And a large share occur at crossings equipped with functioning lights and gates, which means the warning worked and the driver went around it. The safety campaigns reach for the comparison because nothing else lands. A loaded freight train against a passenger car is a mass ratio in the thousands to 1, roughly what a car is to an aluminum can. There is no version of that collision the car survives on physics. The only variable is whether the collision occurs. Heavy trucks are their own category of problem. A loaded tractor trailer needs something like 14 seconds to clear a single track from a standing start, and more than 15 for a double track, which is longer than most drivers imagine, and far longer than the warning time at many crossings allows for a vehicle that stops on the rails. Low-clearance trailers hang up on the hump of a raised crossing. Long trailers get caught in the geometry of a skewed crossing on a narrow road. Every year somewhere, a crew comes around a curve at track speed and finds a truck stranded across the rails with its driver standing beside it, waving. Those are the collisions that make the mile feel less like a statistic and more like a sentence being read out, which is what makes the engineer's position so peculiar. He is operating the only vehicle on the road network that cannot swerve, cannot meaningfully brake, and cannot arrive anywhere unannounced. He is also, structurally, the person guaranteed to watch it happen. Ask railroaders about it, and you will find that a great many of them have been through it. A car, a trespasser, someone who wanted it to happen. They talk about the seconds beforehand more than the impact. The horn, the hand on the handle, the awareness, well before anything touches anything, that the outcome is already determined, and there is nothing left to do but hold the controls and be present for it. That is the real weight of a mile. Not an abstraction on a safety poster. A specific length of time in which a professional watches physics complete a sentence he started too late to change, through no fault of his own. So, one last pass over the ledger. The mile is not a design failure. Every piece of it traces back to a decision that was correct. The air brake's fail-safe logic is one of the great safety inventions, and it costs propagation time. The slack in the couplers is what allows a single locomotive to start 15,000 tons, and it costs braking distance. The tiny hard contact patch between wheel and rail is the reason a railroad can move a ton of freight hundreds of miles on a gallon of fuel, and it costs adhesion. The conservatism in the braking curves costs schedule and buys margin. Take any one of those away and the train stops shorter. It also stops being a train. It becomes something that cannot start its own tonnage, or cannot survive a broken hose, or burns 3 times the fuel to move the same cargo. The mile is not a weakness in the machine. It is the receipt for the machine's strength, and railroads long ago stopped trying to argue with it. They built signal systems around it, wrote rule books around it, spaced crossing circuits around it, and taught generations of engineers to run a train by looking 1.5 miles ahead of where they actually are, which leaves exactly one part of the system that has never been engineered around the mile and never can be: the driver at the crossing, the person on the ballast with headphones in. The pedestrian who assumes a machine that large must be able to stop for them, because everything else on the road can. The next time the gates come down and nothing is in sight, that is the mile, being spent on your behalf by a train you cannot see yet. It is already stopping. It began a long time ago, and the only question that has ever mattered at a grade crossing is not how fast the train can stop. It is whether you are still there when it finishes.